we can move on to the next talk on EMC squared, the Earth Model Column Collaboratory.
Okay, I guess I need to stop sharing, right?
Yep, but thank you very much.
Okay, thank you.
Okay. So, hello everyone. Yeah, go ahead, Adam.
No, I was just gonna say, Israel and Bobby, yeah, please go ahead and share your screens and.
Okay. Just a sec. Okay, so you can see my screen now, I suppose.
Yep.
Good. So hello everyone. Thanks for coming here today. I will present to you first of all a brief overview of our LiDAR and radar simulator and subcolumn generator, EMC squared, the Earth Model Column Collaboratory. I will describe the typical workflow, and then I'll move on to the demo. And this is a work that was mainly developed by me and Bobby Jackson, who is also here. Generally speaking, we need instrument simulators in order to bridge observations and models, in order to allow us to perform direct comparisons, or apples to apples, as we like to say. And the reason is that many instruments have their own sensitivities, their own limitations, and we need to consider that when we compare and evaluate different types of models. Now, EMC squared is an open source ground-based LiDAR and radar simulator, subcolumn generator, which is specifically designed for climate models, but it's also applicable for high resolution model output. And this is very useful in the case that we want, for example, to do model intercomparison projects and evaluate climate model SCM, single column model modes, and compare them also to large eddy simulations model, for example. Now, EMC squared provides flexible framework enabling direct comparison of model output with ground-based and radar and LiDAR observations. And it enables the emulation of ground-based, ship-based, or air or spaceborne measurements, and quite easily. And it uses either a single particle or bulk particle size distribution lookup tables in order to perform the forward calculations. Now, there is more to that with regards to the logic that we're using in order to simulate LiDAR and radar observables, but the main point is to be faithful to the actual physics implemented in the models that we use. And I would note that EMC squared is a software that is fully written in Python, so it follows the general idea that we're following throughout this workshop. Now, with regards to the standard workflow, so what we typically have is we have a model output file. In this case, I'm showing you here model E3, which is NASA's GISS climate model, but it can be E3SM, it could be other model. And we want to compare that to an observations we have, for example, arm observations of the edges around. So what we can do with EMC squared is to bridge between those two different data files. And in order to do that, we first of all invoke and generate a model subclass. And EMC already includes full support of E3SM, CSM, NASA GISS model E3, as well as WRF. And we also need to generate an instrument class. And in this case, we already have full support of the different arm radars. And when I'm referring to support, I'm referring to instrument characteristics, sensitivity, etc., that we need in order to simulate these observables, in order to see what would a radar similar to KZER, for example, or the K-SACR would observe if it was looking at the atmosphere as it represented in the model. You can also see that we have representation for different LiDARs. Again, all of the ARM LiDAR instrument suite, where we also have some additional instruments such as Calypso or NexRad, and it's quite easy to add some additional instrument subclasses, and you're all welcome to contribute. Again, this is a collaboratory project. Now, after we have our subclasses, we move to the subcolumn generator, and this is especially useful for large scale models, and it enables us to emulate a higher resolution in some aspects, sort of like a trade-off between the fact that we don't have a high temporal resolution, and this enables us to perform statistical comparison between mole and observations. However, it can be turned off, for example, when we process large simulation mole output. And I would note that the hydromedia allocation is again consistent with the actual mole overlap assumption. So if we have already our mole class for E3SM, we already consider the overlap assumptions in there with regards to different phase, hydrometeor phase, or with regards to overlying hydrometeors. And I would note that everything is performed by default using parallel processing using the Dusk Python package. Now, after we have the subcolumn generator, we have our subcolumns. We run the simulator, and this is followed by the Hydromedia Classification routines, which are, of course, optional. They're supplementing the mole observation comparisons, and it already includes LiDAR-based classification, that is classification of hydrometeor phase based on the backscatter cross-section versus the linear depolarization ratio. Again, the idea is to be able to run the same routines and compare them all with the observations. And if I'm running a bit too fast, I would note again that this session is recorded, so you can go back and look at it. And of course, feel free to ask questions anyway. Finally, after we perform the classification, we can do visualization, and EMC already includes internal methods in order to plot various types of figures that we can use for our comparison purposes. We already have curtain plots with hatched areas for representing undetectable hydrometeors, as I'll show you in the demo soon. We have the phase partitioning statistics and plots, and we can also produce mean profiles and plot mean profiles and time series. So I'll now just move on to the demo notebook, and let's assume that we have a mole output from E3SM. In this case, this is a regional output and we want to evaluate the mole against and compare it against or compare it with actual measurements from the North Slope site at Ogiavik in the North Slope of Alaska, and we'll use EMC squared in order to perform this comparison. We have either a radiation logic approach or microphysics logic approach, and you're welcome to look at our GMD paper, which we provide a link for at the bottom of this notebook. You can see the manuscript as well as the documentation and the source code, which is our GitHub page. So when we want to use EMC squared, and if you want to know how to install it, again, I would suggest just looking at the EMC documentation or the GitHub page. So we first begin by importing our packages. We import EMC squared, we import matplotlib, we import NumPy and Xarray, which you already were briefly introduced yesterday, and some of you may already be familiar with that. And after we load these packages, we need to initialize our instrument class object. So the fixed site at Ogiavik has a quasar, and we want to compare the mole output against quasar observations. And also, let's say we also want to compare to high spectral resolution LiDAR HSRL measurements, which was deployed there until July of 2019. And we first need to create such an instrument subclass. So you can see the lines of code here. It's pretty simple, pretty straightforward. In the case of the quasar, we also specify the site, and this is important since we want to have the actual sensitivities of the quasar that is deployed at the NSA. It has different sensitivities, for example, from the quasar 2 that is deployed at ENA or the one that is deployed and on the AMF 2. So when I run this cell, I can see that instrument class generation is done. I can also, for example, look at the Kaiser class object, and I can see that it says that this is an EMC2 instrument class or subclass called Kaiser. We can also look at all the methods that this object has, and these are methods or attributes. So we can see that we have some place for the PR noise, for the scattering lookup tables that we load, as well as some other internal methods. We can see the gain here, the frequency, and so on and so forth. And after we generate our instrument classes, what we need to do then is to initialize a mol class. We need to first of all tell EMC what type of mol are we using, and at the same time we can load the data file. But first, I would like us to look at the output from E3SM, because this is a case. This is a situation that we typically have. And in order to first look at the data file, I'm using Xarray. I'm first of all opening the data with Xarray. Now, you might have seen it yesterday, and probably we also talk about it on Friday. I saw that there's another session for Xarray, and here we see a list of all of our data variables. And on this column here, we can see the different coordinates, or the different dimensions that these mol output have. Now, the issue with E3SM output, as an example, is that first of all, it operates on a cube sphere grid. And that means that the mol output is not strictly on a latitude versus longitude versus level grid. It is simply provided in different columns. So we typically have an ncol dimension. So we can see that, for example, if we look at average rain number concentration, we can see that the dimensions are time versus level, that is pressure level, versus the column number, not latitude and another dimension for longitude. And we need to be able to consider this when we run this comparison between E3SM and the observations. Now, in addition, you can see that there is some appended string to the dimension that we have in the E3SM output, and that is the result of the machinery related to E3SM. So what we would typically want to do is to first of all tell E3SM that this mol output does not have a latitude versus longitude. It only has a column output, and we wanted to inform it that it has some appended strings that we would like to remove when we read it. So EMC squared does have these internal methods to do that. So what we do here is we create an E3SM mol class. We inform it with the path to the output file that we have. We tell it that all the appended spatial information is in what we refer to as the latitude dimension. This is part of what we do when we specify a mol class. And we also tell it that we have some appended strings that need to be removed. So when I run this cell, you can see that we receive a message that this is original output data set, and it's stacking the time, latitude, and longitude dimensions for processing with EMC squared. And the reason is that it's more easy to process regional output by first stacking the different dimensions and then unstacking them when we finish with that. But EMC also has internal methods to do that. What we can see here is that when we look at the data variables, we no longer have this appended string. We do have a dimension that refers to the time lat lon, and that basically the fact that we stacked both the time dimension with the latitude and longitude, or in this case, the time with the column string. And you can see that the names of the different variables no longer have their appended strings stating the region that was cropped from the global mol, and we can compare that when we look at these output fields in the original output file. So after we have we generated our mole class object, we generated our instrument class object. Now we can run the subcolumn generator and instrument simulator. And what we can see here is that we first need to specify the number of subcolumns. And we would typically use 50 or 100 because that means that we can generate better statistics if we want when we compare the observations with the mole. And what we do here first is we call the we generate again. We tell the EMC to start processing the data, and we first do this by specifying the mole class that we formed, the E3SM mole class. Then we say that we want to use the AGSRL instrument class to do the forward simulation. So we inform EMC squared that we were actually processing LiDAR data, and we're providing here the number of subcolumns that we want. We also wanted to run all the related classification routines in sort of a post-processing after the simulator is finished running. And what we're doing here is we're saying that we want all the zeros to be converted to not a number values after processing is done, and that refers only to the classification routines. So here we're basically running the E3SM, the LiDAR processing, but we also want to generate the radar processing. And in order to do that, we call the same function again, that is the make simulated data method. And what we do here is we specify the Kaiser class object, and we also tell it, because after that we will likely won't call the entire simulator again. We first of all say at the end, when you finish, unstack the dimensions, go back to time dimension on the one hand versus the column dimension on the other hand. And we also say that we want to skip the subcolumn generator because we already called it once. We don't need to do this thing twice. And we also say we also tell the simulator to finalize the fields. And here again, it will essentially convert all the output fields to the zero values in the output fields to not a number, and that will allow us to generate better plots in which the background will be in white. So we can see that after we start running this cell, it starts to create subcolumns. It doesn't have any convective processing because all of the data, all the microphysics are implemented in CLUB, which is implemented in E3SM. That means that we're generally only using the Morrison-Gettleman microphysics scheme, and it says that it's doing parallel stratiform hydrometeor allocation in subcolumns, and you can see that we have how many fully overcast voxels we have here. The total processing time is also specified here. Note that it takes quite pretty long here because we're only using a single core in this simulation, but when you run it on your local machine, it will be much faster. And after that, you can see that we're generating the stratiform LiDAR variables, and we're using bulk scattering lookup tables, again, consistent with the physics implemented in E3SM and in the radiation scheme in order to do these forward calculations. Note that we are also in E3SM, for example, rain is not considered in the radiation scheme, and therefore we basically skip the radiation. We're not including it when we forward calculate the radar and LiDAR observables, since they're based on electromagnetic radiation signals. So now the entire processing is done. We can see that the radar processing is done, and we can look at the output file. So again, we have our E3SM mol class, and when we do the name of this mol class and do .ds, we can see the X-ray data set that is constructed using, first of all, the mol output. But then when we look at the data variables, we can see the output fields from the simulator. So in all of the fields here are outputs directly from the E3SM mol. We can see here grid box average ice water content, for example, We can see here surface pressure, but when we scroll down furthermore, we'll start seeing the EMC square output. So for example, we can see the subcolumn allocation of mixing ratio. We can see the number concentration. And this is, for example, just for the PI class. PI refers to snow or precipitating ice. We can see CL, which is cloud liquid. And we scroll further down. Here the EMC squared start producing fields that refer to the actual LiDAR and radar observables. So here we have the backscatter coefficient from all stratiform hydrometeors. You can see the units. You can see the method that was used in order to do the forward calculations. This is based on David Mitchell's algorithms. We can, for example, see the backscatter cross-section. We can see the optical depth, cumulative optical depth at model layer base. So we can see that EMC also provides a lot of attributes to all the fields that it generates. We can see an extinction mask, which will be used when we'll plot everything. And we can also see now the radar variables. We have the reflectivity, total reflectivity, equivalent reflectivity factor from all stratiform hydrometeors. We have, and we can also have a reflectivity for different hydrometeor classes. So this will be very useful when we'll want to consider and examine the contribution of each hydrometeor class, whether it's cloud liquid or cloud ice or snow, to the total signal that we get from the simulator. And a very useful way to evaluate these data, again, is using visualization. And we can use matplotlib, we can use Xarray's internal methods, or we can use EMC squared internal methods, which are very useful in order to examine the output data. For that, we have a dedicated class object called subcolumn display, which is based on the act display class object. And what we do here in this cell is we first specify our input parameters. You can see we first of all say here that we'll want to generate a figure with four different fields. You can see that we want to see the backscatter procession. This is a LiDAR variable, another LiDAR variable, which is the extinction. We have also the optical thickness observing from the surface. We can also specify in EMC squared that we want to observe the clouds from above. That will be useful for if we want to do some comparison with airborne measurements. And we also say that we want to plot the attenuated equivalent reflectivity factor. So we're also considering some attenuation due to hydrometeors as well as the atmospheric species. Here we specify our color scale ranges, but we can also simply use the default ones if we want. The range of the y-axis, we specify whether we want log scale plots that the color scale in which the color scale will be in which the color scale will be plotted in log scale or not. And we should also specify whether this is a radar field or not. Finally, I'm also specifying what are the north slope, the Ugyavik site coordinates, and that will be useful since we call that we're using a regional mole output. And when we plot, we want to plot subcolumns, for example, associated with a single coordinate. So what we first do is we call this subcolumn display object. We first of all generate this object, and this is a rather similar text to that is used when we use matplotlib. We want to generate the subcolumns and subplots, and we're saying that this is the shape we want. We want one row of four different subcolumns. We specify the figure size, and we also specify the coordinate, the latitude and longitude of the coordinates. And we also specify that we want a tight layout. Now we also specify here data masks in order to mark in the figure regions that are not detected by the radar or LiDAR. And as you can see, EMC square already produces these fields refer to extinction mask for LiDAR, and also another field called detect mask. This refers to what is detectable with the quasar. And now we are having these lines, a short loop at which we basically call the plotting routine, the plotting method called a plot subcolumn time series in order to plot the different each of the different axes. So here we specify what field we want to plot, the color map, and again, these are optional input parameters. And we also specify what the mask array that we want to use, as well as the fact that we want hatched mask to be plotted as well. So we can see the figure here. What we can see here is 1 day of E3SM output corresponding to 1 day of the MAL simulation. So this is 1 day. We can see here that we have what appears to be a frontal system. We can see that we have a nice liquid layer, and on the y-axis here we have the pressure level. So we can see that we have a cloud up to 2 or 2.5 kilometers. And all the hatched regions are regions that we would not be able to detect with an HSRL. And the same thing for quasar. You can see that here we have the reflectivity, but the topmost reaches of the cloud of the frontal system here, we could have not detected it with an actual quasar. So here we have the backscatter, extinction, optical thickness, cumulative optical thickness, and the reflectivity, if I forgot to mention that. Now, another feature, as I mentioned with E3 with EMC squared, is the fact that we can perform some phase classification. We can plot the phase classification output, and by using the same methods, we can compare with the actual observations. And we can also use the different columns, subcolumns that we generated in order to calculate phase ratio statistics, phase partitioning. So EMC squared has internal method to calculate phase ratio, and we tell it to use the HSRL phase mask output. And again, we generate another subcolumn display object. Again, inform it with the latitude and longitude coordinates, which will be the closest coordinates corresponding to the MAL output that we want to plot here. And again, in one of the axes here that will generate one of the panels, we'll first want to plot the HSRL phase mask. And you can see already this phase mask here. We have 4 different classes. We have ice, liquid, and 2 different undefined phases here. And I removed here all the regions that are not detected by the HSRL, by our simulated HSRL due to attenuation or full extinction of the LiDAR signal. And this really resembles what we typically see in observations, and you can just go to the ARM archive and you'll quickly see these quick looks that seems rather similar to what we observe. We have these ice phases, and the liquid signal is typically rather thin because the LiDAR signal gets extinguished right after encountering a liquid layer. And below this panel, we want to plot the frequency phase ratio that was generated by EMC squared. So you can see here this frequency phase ratio. So while here we plotted in the HSRL phase mask, we plotted the phase mask corresponding to a single subcolumn. In here, we're using all of the subcolumns in our MAL grid cell, in our E3SM MAL grid cell, in order to calculate these phase ratios. So you can see that the MAL output consistently says that we have liquid layer here. And this is a very nice demonstration or representation of how the MAL observes the atmosphere and how close it is to what we see in actual observations. Now recall that we can also plot these 4 different variables for each of the 4 hydrometeor classes that we use, or 3 hydrometeor classes that we use in this case. This, first of all, enables us to evaluate the classification methods. For example, if we look at the backscatter cross-section for the liquid, we can see that indeed we have pretty good overlap between what the MAL says the actual truth is with regards to cloud liquid and what is actually represented by EMC squares EMC squared phase classification routines that again can be applied to observations as well. So we can see here a breakdown of the contributions of these different variables from cloud liquid. This is the first raw. Second raw represents cloud ice, and the third raw represents snow or precipitating ice. Now, in addition, as you saw here, what we did is we plotted a time series of corresponding to a different subcolumn. What we can also do is use the plot single profile method in order to plot all the subcolumns at a given time step. So here we specify the time at which we want to plot the EMC squared output. And as you can see here, we can see all of our 50 subcolumns that we specified, plotted as a function of pressure level. So we can see that we have several, quite a lot of levels where we have fully overcast sky, but the liquid layer, for example, is not fully overcast. We do have, even though it means that our the liquid cover fraction or liquid fraction is on the order of 0.9 or something close to that. Now, finally, we can also see that we can also use EMC squared to plot mean profiles of different variables. And in here, we use the plot subcolumn mean profile. Again, we can specify the x-axis range that we want. We can specify title. We say that we want, in this case, to plot the profiles not as a function of pressure level, but as a function of altitude. And for this reason, we specify pressure coordinates equals false. And what you can see here is we have, again, the backscatter cross-section as a function of altitude. Same thing for extinction cross-section. These are, again, HSRL output fields and the cumulative optical thickness. And what you can see here, this envelope refers to the mean plus minus the 1 standard deviation, and the mean is calculated based on all the subcolumns that we have in the actual mole grid cell that we're plotting. And we also have here the reflectivity. You can see that we have here a break, of course, because we don't have any hydrometeors there. And you can see that we don't have a lot of variability with regards to the reflectivity. In this case, again, we can use other schemes that we have, the microphysics scheme logic when we do EMC squared processing. And again, I know that some of the terms that I mentioned could be confusing, and I would also refer to the GMD paper that was recently published, in which we describe these logics and the general approach that we use in EMC squared. Again, we have here some resources and references, and you're welcome also to contribute to the different processing and different routines and what we're started doing here. So thanks for your attention.
All right. Thanks, Israel. Do we have any questions?
Can I add too? We are also we welcome any contributions from the community for this. I designed EMC squared. Like, we both went through, designed the model and instrument objects. So you can just add your own model or instrument into there with the assumptions from your model and import it into there. We gave a very standardized structure for doing so. So we try to make that as easy as possible, but don't hesitate to contact either of us about that.
Yeah.
Okay. Thanks, Bobby. That was actually one of my questions was, is this really just LiDAR, radar oriented, or is it something where we could put in, ARM has a lot of instrumentation out there. Is there options for, or ways we could get the other simulators in here that aren't radar, LiDAR oriented? Does that fall in the scope here, or is that outside the scope?
We have a ciliometer in there. As far as, I don't think we've discussed anything outside of active remote sensing at this point. We could potentially see about trying to simulate those other variables, like, for example, from radiometers or something like that. But right now we are just radar, LiDAR, ciliometer.
Okay. All right. Are there any other questions? And feel free to follow up outside. This was definitely very interesting. It's great to see this work.